If you look at this question, this is the goodness of fit. So they tell you randomly selected 140 convicted criminals reveal the crimes committed on the following day. So from the 140, 21 committed on 17 committed on Monday, 21 committed on Tuesday, and therefore. Test and null hypothesis underlying the population crimes are equally likely. So, when they say compare this to something else that, like a common knowledge, equally likely, we think that, well, there are 7 days, it's supposed to be, each one of them is supposed to be one of 7 of the total. So this is what we expect. 1/7 of 40 would be 20, 20, 20, 20, 20, 20, 20. So we expect that it's supposed to be 20, 20, 20, 20. Is this true or not? So you say, no, the observed values do not agree with the expected values, and here we say yes, it does, or they do. Test, cut. Still O minus E squared over E, but that's goodness of fit. Goodness of fit when you compare numbers to numbers we expect, or percentages to percentages we expect. In terms of decision rules, I told you for chi is standard, if chi is more than table reject. They give you alpha at 1%. Now degree freedom for this would be number of categories minus 1. It's like sample minus 1. A little bit different than the other one. So you go to your chi table. And the common number between 1% and degree freedom 6, 1681. So we do the calculations. Now the calculations for this is easier at least than the other one. What you need to do is you find, this is the given number I told you is always the observed, and we have the expected. So what you need to do is apply the formula. Take the difference between them, square it, divide the expected, plus the difference between them, square it, divide expected. The difference between them, you square it, divide expected. The difference between them, you square it, divide expected. The difference between them, you square it, divide expected. The difference between them, you square it, divide expected. And the difference between the last two, you square it, divide expected. If you do this, this will give you 3.4. So you're ready to make a conclusion. Your chi test, we calculated 3.4. That's not more than 1681. It's not more. In this case, we are not going to reject H0 because it's not satisfied. We're not concluding HA. Anytime you're not concluding HA or you're not rejecting, you have to say type 2. When you reject, we say type 1 risk alpha. Here we say type 2 could be committed and risk equals beta. You don't need to calculate it, just say risk equals beta. In English, you're not concluding HA, so we don't have evidence for HA. So we don't have evidence that expected and observed agree with each other. So we don't have evidence that they agree with each other. If you're asked for the p-value, again, you go to any website, just type in Google chi-square p-value calculator. They'll ask you for the degree freedom and alpha, and that will tell you what the p-value is. It will be more than 5% in this case. So, this is the answer for this question. Now, we will go to the next one. So the chi would be similar to one of the two questions we did, but it's probably the first one. I don't see a goodness of fit question, but again, it's not hard. It's actually easier than the other one. The next question I'm going to do is the ANOVA. It's a question number 1. It says, senior partner and brokerage firm wishes to determine whether there is really any difference in long-run performance of different categories of people hired by the firm and they divided them into customer representatives. They have junior members classified into four groups. Professionals, recent business grads, former salespeople, and hired people. So they give you the numbers. If you look at the table, professional, you have 6 different professionals, and they give you the ratings for each one of them. You got 6 people, business grad, and you have the rating for each one of them. And the same 6 for salespeople, 6 brokers. Question: at 5% level of significance, is there any difference in the average performance of the 4 types of customer representatives? Use classical and use Excel or Minitab. It's all the same. How do we know it's ANOVA? Well, first of all, we know it's chi. It's not counts of people. All these numbers are ratings. They're not counts, so we know it's not chi. Anytime you compare 3 groups or more, we use ANOVA. So basically, ANOVA is used when you compare 3 groups or more. And here we're comparing for ANOVA. But the only thing left is you need to determine whether this is double ANOVA or single ANOVA. So single, also called one-way ANOVA, or is it double ANOVA, or block ANOVA, or two-way ANOVA. So you ask yourself, do we have the same 6 people under professional? Are they the same 6 people under business grad? Are they the same people under salespeople, or we have different people? If you have different, then you're single. If it's the same group across, then it would be double. It'd be like they will indicate that there are 6 here and there's the same 6 here and the same 6 here. You'll see that in a later question. So we know it's single ANOVA. So once you realize that you have single ANOVA, in H0 you say mu group 1 equals 2 equals 3 equals 4, meaning the means of ratings are the same for the 4 types. HA would be at least one is different. Test. For single ANOVA, it's famous, the F test, and it's MS effect over MS error. Decision rule. ANOVA is always like this. If F more than or equal table, reject A0. What is the number, or how to get it with the table, and how we find this number, leave it for now. We'll come back to it. So we go back to the question. It's time to do the analysis, and I have this in a different picture. It's the picture labeled, it looks like coming from Excel, and on top labeled ANOVA single. I'll show you what it is, and I'll tell you exactly how I think she'll ask the question. So you have the ANOVA table. First is your source, and it's supposed to be SS between. They also call it the SS treatment. Then the SS error, they also call it the SS within. And you also have the SS total. The value of the SS will be given. In the table here, you're given all 3. But she will give you 2 of them. She might give you the first one, say 255 6 4583. Or 8. And maybe the last one. 3330625. And this would be missing. Then you have the degree of freedom. Then you have MS. And then you have the F number. Okay. The degree freedom, if you look at it, it's 3, 20, and 23. I'm going to assume that none of these are given. And none of the MS's and the F test is not given. And that you have to complete the table in order to be able to do this. Okay. You always start here. You start with degree of freedom. For the between the treatment is number of groups minus 1. Remember, there are 4 different categories, so it's 4 minus 1. That's why the degree of freedom for the first one is 3. For the second one, it's the big sample minus number of groups. The big sample, altogether you have 24, minus the 4 groups, this one is 20. Here, the total, you just add them, gives you 23. So you always, if you need to fill in the information, you always start with the degree of freedom. She might give you one of them. If not, finding them for single ANOVA, very straightforward. We're also missing this number, but just remember, the first 2 add to the total. So if you minus them, 333 minus the 2, 5, 5, 6, 4, 5, 8, that gives you the missing one. So the first 2 always add to the total. And the missing one is 774 167. We're also assuming we're not given MS. MS is SS over degree of freedom. So this one over 3, this one over 20. You don't need the total anymore. So if you divide the first one by 3, you get this number, 852 153. And 774 over 20, you get the other number, 38708. And then the test, you just divide these 2 numbers. So the MS, you go this over this, and the F, you just divide the 2 numbers. You divide the 2 numbers, you get 22,0147, and that's your F test that you're going to compare to the table. The problem is, we don't have the number. We know, according to the question, if you guys remember, it was at alpha 5%. So I know that alpha is 5%, 1%, sorry. I know that alpha is 1%. But that's not enough. I also need to know degree of freedom. Now, the degree of freedom for this question or this type of question, there are degree of freedom going this way, and there's a degree of freedom going down. The degree of freedom going this way is the degree of freedom for the between. And the one going down is for the 20. So it's like 3 this way, 20 down. Again, she probably give you the F table. So I'm gonna use the F table. So I'm gonna go to Google. I'm gonna look for the, say, F table. You'll see a lot of F tables. But if you go to see the common area between 3 and 20, so 3 this way, 20 down, 320, I have this number, 4.93. I don't believe that's true. And I don't have the table that she's using. I think that the number, when you look it up, it would be around 3. I remember vaguely that it's actually it tells you in the Excel what it's supposed to be. So find the table you're using. It's easy to see what it is. So if I go back to the picture, if I go to the Excel, it tells me F critical. You see the F critical, that's the number you're supposed to get from the table. So the number from the table would be 3.09, and that's the one you get from the table. You see it in Excel. So we are ready to make a conclusion. Your test is 220147. That's way more than 3098. So the condition here is satisfied. We are going to reject H0. We are going to conclude HA. And again, anytime you reject H0, you have to mention type 1 could be committed. So type 1 could be committed. And the rest equals alpha, and it's whatever given in the question. It was 1%. If you're rejecting H0, concluding HA, then at least one is different. So we have enough evidence to show, you have to put it in full sentence, we have enough evidence to show at least one group is different. And again, if you're asked to find the p-value for this, put F table p-value calculator. You will see the one that tells you what's the degree freedom numerator, degree freedom denominator, what's the alpha, what's the F naught, what's the calculated test, and it will tell you exactly what your p-value is. Okay. This is the end of part 2. I'll stop now, and when I come back, we're going to do the ANOVA double or two-way ANOVA blocking system.